Okay, welcome everyone. This is our 10th adventure in deep learning. We are deep learning adventurers, that's the meetup name. And we have been taking this specialization from Coursera called TensorFlow in Practice. And today you're going to hear a little bit about how to use TensorFlow and deep learning to do forecasting for time series. So my colleagues and co-hosts, David and Robert, are going to talk about a little bit about what are time series, how can we use statistical methods, and how can we use also deep learning methods like regular neural network or recurrent neural network or convolutional neural network and things of that nature. Before we start, just some brief overview of who we are and what we do. So again, this is a meetup, a growing community, a very active community. We have a meetup page, a GitHub repository that I pushed a lot of updates recently, and I'll talk about them later. And we have a Slack page in case you want to join us. And if you are new to this meetup, all our previous sessions are actually recorded and available on YouTube at this bit.ly deep learning TF. TF stands for TensorFlow. I saw a lot of new members today, so maybe I thought it would be a good idea to just quickly go over the room and introduce ourselves and just say a little bit about what we enjoy doing or what we're interested in learning. So this along the way. So I'll kick it off and I'll call people if you don't mind. So my name is George and I'm a regular member of this meetup, and I enjoy using deep learning for different interesting problems, especially NLP and computer vision. And today and this month, I'm super excited to learn more about time series and forecasting. With that said, I'll kick it off to David.
Hi, yeah, I'm David Patton. I'm the another core organizer of this group, been here since day one. And I've actually finished the course that we're covering here and am heavily involved right now in the another course from deep learning about TensorFlow called Data and Deployment. So another course there. And I'm going to kick it off to somebody else.
Robert?
Hi, my name is Robert. I'm a regular member of the meetup and co-organizer as well, along with George and David. Bit about myself, I enjoy playing the piano and am interested in learning more about deep learning models. That's what this course is all about. I'm particularly interested in computer vision, sequence models, and neural networks, or NLP, I mean.
Cool. Peter Tracy?
Yes, I'm here, but I am looking for another job right now because I lost my job last week because I want to learn about this. And I like you guys. Thank you much.
Cool. Thank you for joining us. Martin?
I'm Martin, and I'm interested in machine reading comprehension, and I'm also interested in brain modeling and also kind of real neuroscience related machine learning.
Interesting. Jess? We'll come back to Jess. Vishal Oza? Okay. Suvarna?
Hi, I'm my second meetup actually, and I've done Python and I'm just exploring deep learning and all the machine learning things. And last time I enjoyed your TensorFlow last week actually.
Awesome. Good to see you back.
Thank you.
Julio? Julio Montesino?
I have some problem with the audio, but I'm
We can hear you.
very happy with being with you, and I'm interested in using TensorFlow in the future. So I just want to hear a little bit more than what I know and see how to use it.
Cool. Welcome. Si Sheng?
Hi, my name is Chen. I'm new member of this meetup and enjoy watch movie and interested in learn more about the deep learning.
Cool. Welcome. Peter?
Yes.
Hi. Yeah, I'm Peter. I'm a regular member here, and yeah, I'm looking to learn anything I can about machine learning, deep learning, and looking for some applications at my job.
Cool. Sienna and Piper?
Yeah, that's a leftover from my children doing online learning. My name's Mark Christensen. I have a general interest in all this. I took Andrew's first 5 deep learning courses. I thought they were very, very good classes. And I just found out about your meetup. I'm very interested in seeing what you guys do. I don't have a particular area of focus right now. I'm looking to maybe learn more about NLP. And yeah.
Good to have you. Welcome.
Thanks.
Tanvi?
Hello everybody, I'm Tanvi and I'm a new member. I found this meetup accidentally, I think so. But I'm glad I found it. I recently completed my master's in data science this spring and I want to continue learning. I'm mainly interested in like NLP and time series. My capstone project was in time series. So that got me more interested in this. At work, I've done a little bit work on TensorFlow validation framework. So I thought maybe I should be able to catch up a little bit more over here.
Cool. Awesome. And congratulations on your graduation.
Thank you.
Yefim?
Let's see.
Samuel. I'm sorry, I have my 6-year-old here. Yefim Shuf. Let's see, I'm new here, first time. Found you guys through Meetup. Looking forward to learning more. I have some experience in machine learning.
Welcome. Hopefully your kid can join us.
My kiddo has experience in learning, not through machine, but through me. Looking forward, guys.
Cool. Thanks for joining us. And Will? Will, are you there? Okay. Cool. Maybe some audio problems. Thank you everyone for sharing. I find it really interesting as a group to get to know each other. So I appreciate that.
George, can I make a quick announcement?
Yeah, go for it.
So based on what I was hearing, on our Slack channel, which I encourage everybody to join if they haven't, keep the conversation going there. But I created an opportunities channel for people that might be looking for a job or want to post a job they have open, or if they're looking for team members on a project, volunteers or whatever, just a place for people to maybe help each other out there.
Awesome, man. That's a great idea. Yep. Thanks for doing that, David.
Sure.
Cool. This is just an overview that we're not a typical meetup. We try to make learning engaging and fun, and we have something called deep learning trivia that in the end of each course, we as a group take it together. We can also take it offline, but think of it as an engaging way to really go over the concepts that you learned and also have a little bit of fun while learning new things. So I haven't put together the one for this course yet, but hopefully by sometime next month I should have it. Cool, and this is just a slide on the content and attribution that most of our screenshots and most of our slides are actually coming from Coursera and Deep Learning AI. So I want to make sure we have the attribution to those companies. And this specialization, it's actually on Coursera. If you're new to TensorFlow, you've never heard of TensorFlow, this is a great specialization to start with, or if you're actually new to deep learning. If you already know about deep learning or TensorFlow, there's an advanced version of this specialization called data and deployment. We plan to take that after this specialization. So this TensorFlow and Practice Specialization is made of 4 courses: an introduction to TensorFlow and AI, computer vision and convolutional neural networks, natural language processing, and the one that we're going to kick off this week is sequences, time series, and prediction. So if you haven't been able to join us before, again, we have all our previous sessions recorded on our YouTube channel that you can follow up. In terms of setup and in terms of what environment do many of us use? We use actually Colab, which is a free resource offered by Google. It runs on Google Cloud, and think of it as Jupyter Notebook, but it runs on the cloud. You don't have to provide your own CPU. You can even have a GPU or TPU available for your coding. And if your training doesn't last more than 12 or 24 hours, you should be good. If you have a huge data set or a huge complicated model, then you definitely need to use a virtual machine on any of the cloud providers. Cool, so this course 4 is made of 4 weeks. And in week 1, we're gonna take a deeper dive on what is actually time series, what is a sequence, and how can we use statistical methods to actually do prediction and forecasting. And David will take on week 2, which is using a deep learning approach to actually do the same, to solve the same challenge of forecasting for time series. So in terms of sequence and prediction, what is a time series? When we say time series, we usually mean an ordered sequence of values. Usually they're equally spaced. They don't have to be, but think of it as what is the temperature during the day, or what is the stock price during the closing price of a stock during a week, or what is something that's equally spaced over time. That's the time series. So that's the x-axis basically that we see here on this chart. If the y-axis is made up of only one value, if we are recording only one value at a given time, then we have something called the univariate time series. Uni means one. So this is basically a simple plot of a univariate time series. We have our x-axis, which is usually time, and our y-axis, which is the value of the time series. If we have multiple values for a given time step, let's say we might have temperature, humidity, air pollution, you name it, then we have something called multivariate time series. And you'd have a graph that basically looks like a multiple series over here. And just an example of a time series here, you might be interested in the weather or precipitation or wind or traffic or air pollution. That's some real life scenarios or real life time series. When looking at multivariate time series, you can superimpose them and you can look at them together. For example, this chart here has x-axis as time, and it's actually tracking all the way back to 1880s till 2020. On the left axis, you have in blue and red the global average temperature. And on the red mark here, you actually have the CO2 concentration is also on the secondary y-axis. So this is one way of actually looking at multivariate time series. Another way of looking at them is you can decompose a multivariate time series into simpler ones and plot them separately. So Lawrence, in his course, he gave this example of a time series where you're actually tracking the position of an object, let's say a car. And if you track the position of a car every second, let's say, based on the speed and acceleration of the car, assuming that it's not constant, you will have a sequence of latitude and longitude or location measurements that are not equally spaced in distance. They're equally spaced in time every second, but they're not equally spaced in distance. And if you plot the latitude and the longitude here, you'll see that they're actually they're actually made up of univariate time series. I was trying to figure out, since the car, if assuming that up is north and left is west and right is east and down is south, I was trying to figure out if this graph made any sense or where in the world is this car. So as a trivia, think about it, what is the longitude and longitude and latitude and coordinates, and can you have an idea of where in the world this car is or is going? Because based on this chart, it actually can only belong to a specific, what is called east or west hemisphere or north or south hemisphere. Again. This is just another time series. I found this this really interesting graphs here on safegraph.com that I wanted to see some patterns or some more real life scenarios basically of trends. So what I look for is what is on the y-axis. On the x-axis we have time, and on the y-axis we have what is something called relative foot traffic, or basically visits. And we have two time series. In orange, we have the 2019 time series, and in blue, we have the 2020. So you can see, for example, that 1 means basically that that in the data set here, the sit-down restaurants didn't participate. They're pretty consistent or pretty full. Like they don't have a lot of empty tables. And you see in 2020, after the outbreak hit us, that it's significantly lower. It's actually dropped close to 30%. And it's trying to pick up. Right now, I think it's at 70% for these data sets. But I'm not sure how long it will take to get back to normal. You can also see the impact of the outbreak also in the stock market. If you're interested in finance or general time series forecasting, you can see that the outbreak has impacted not equally, but at some level, most indexes globally.
George, just curious about that foot traffic chart. Do you know what the denominator is, or what the 1 represents? Is it relative to the first day of January, or is it relative to some previous year? Do you know? Just curious.
Usually it looks like that. Usually, when you do percent-wise graphs, I think this is what that is. Either that or maybe capacity. Could also be capacity. I have to look at the legend here, but I either compared to January 1st or capacity, I would say. Again, some of them are over capacity. That means people had to wait. But then again, it could also mean that it is 20% higher than the January value. Yeah, this is more relative. This is not, this is relative. So based on January 1st, where are we now in this chart? But I think this could also be relative to January 1st. I'll have to take a look.
I suppose if they all start right in the same place, then it's probably relative to January 1st.
Yeah, it looks like that. Yeah, then this is looking at different industries. This is looking at airports, bars, coffee places, sit-down restaurants was one of them that we looked at. General merchandise, hotels, movie theaters, supermarkets. And you can see that many of them are actually coming back but there are some other ones, for example, like airports in blue or movie theaters that still, I would say they're close to 0, right? I mean, at least where I live. Different brands, you see some of them are sticking out more than other ones. For example, Home Depot compared to other brands, different regions in the US, as well as different restaurant categories. I found that interesting chart. This is just to motivate us a little bit of what are time series, and actually we use them every day, and something that we can also use for analysis for our own models. Cool. So given a time series, what are some machine learning or deep learning or in general statistical methods we can use, or actions we can take to actually do something with the data in a time series? So the first action or the first outcome we can do is something called forecasting. That means that given previous historical information, let's say each data point here is actually a day. So given historical information for the last probably 3 years here, given that a year has 365 data points, can we predict future values? And predict meaning, can we estimate or can we derive what is the future values a day, a week, a year, as far as we can? As you know, in forecasting, the further we go into the future, the more uncertain and the less sure we are of our predictions. So in this chart, we're predicting from time step 1,000 till time step 1,500. So we're predicting about 1,500 steps. Another function or another outcome we can do given time series is something called imputation. That means that given all the data that we have right now, we might have some gaps in the past. And can we use some kind of a model to actually forecast back in time? That's one way of looking at this time series. So I think these two problems are very, very related, right? One way is you can do forecasting forward in time. if you do forecasting backward in time, you're probably going to get this imputed data in the past. That's something I found interesting. Something else you can do with time series is something called anomaly detection. So let's say you have users visiting a website or traffic around your area or electric usage or water usage, you name it. If you see a spike all of a sudden for a week or a month or a day, then you know that something is off and you need to investigate. Maybe in a website traffic scenario, maybe there's a denial of service attack. Another example that Lawrence gave in his course was imputation, but not just for past values. It was imputation for missing values. So what he's plotting here is on the x-axis we have year, and on the y-axis we have density of computer chips. So he's actually plotting here what is called the Moore's law, that every 18 months the density doubles of computer chips. And you see here, this is log scale. So it actually is 10 times more. One grid line is 10 times higher than the previous one. So if you plot a linear line, it's actually exponential line in linear scale, but it's linear in log scale. And you can see that the actual values of this density of chips actually pretty closely follow this linear trend. There were some years that there were no data, or maybe there were no chips released, but using imputation, you can actually kind of predict what those values should be, given the trends and the patterns that you see in the overall data set. What other things can you do with time series? This is a time series of a recorded voice. One challenge would be to go from raw audio, to actually figuring it out, what are the actual words that are spoken behind each word. I'm not sure if the words and the patterns match here, but think of it as if you record yourself and if you play back in a software, you're going to see this these patterns. And one challenge would be, can you actually detect the word that was said? So this is an active area of research, and actually you see a lot of products like Google Home or Alexa or Siri or even on your phone that do this speech recognition and also speech generation, where you go from text to speech. Any questions before we start with the technical part of this? Okay. So let's define some common patterns and some common features that most time series have. So we know for sure that we're going to need a time axis. Now, in terms of values, those values can take and can be any number. So, but most time series have many features, many patterns, in common. One of them is called trend, and think of it as a slope. So, for example, what we're looking at here is time steps, and the y-axis is basically a trend or a slope version or a scaled version of time. So how do we derive that? We have time as 4 times 365 plus 1. Think of it as 4 years of days, 4 years of time range. We have, we're calling here this function trend, which is basically takes 2 inputs, the time and also the slope. And the slope in this case is just 10% of the time scale. So in this case, if you look at the numbers, 1400 here, this is 140, it's 10 times less. So the trend is basically the values are 10 times less than the time values. This is just a simple trend. Another thing you can plot and visualize is something called a pattern. This is more of a regular pattern, but think of it as when you look at average temperature, there's a seasonality, there's a pattern to it, right? It gets cold in the winter, it gets hot in the summer, somewhere between in fall and spring. So what we're doing here is we are defining this seasonal pattern through cosines and exponentials. And what we're doing here is we're trying to figure out a period that, let's say, every 400 units or every 300 something units, we actually repeat the same pattern. So there's a pattern that repeats here. It's very mathematical, as you can see. there's a concept called stationarity that Lawrence briefly touched upon, but I just thought to explain a little bit better here. If you come from a mathematical background, the technical definition is that a time series or a time process or in general a process is stationary when its unconditional joint probability distribution does not change over time. So that means that things like mean or average or variance also do not change over time. And what I'm showing here on the left is, let's say you have two random variables, x and y, and they have a joint probability distribution, p, x, comma, y. All for this time series to be stationary, this unconditional joint probability does not change over time. So basically your means and your variances and other patterns and other underlying parameters do not change over time. And we're going to see some example here. So if you plot a stationary time series, you'll look something like this. It doesn't have to be mathematical as we saw before, like clearly defined. You can also have something called noise. Non-stationary is one that the mean or other parameters change over time. So you see here, for example, that the mean value of this time series is actually dropping and then it's increasing after this time step. You could have something called autocorrelation. This is a feature in a time series. That means that values in a time series depend on previous values. So the way to look at this is here that this time series is made up of what are called some random impulses. So at some random times you have a high value, let's say 0.2 here. But then for a while, all the future values are actually dependent on previous values. Some kind of exponential smoothing effect, as you see here, that they slowly go down. Then you have a sudden spike, slowly go down. Sudden spike of random magnitude, slowly go down exponentially. Spike, slowly go down exponentially. So autocorrelation is what's causing this behavior of this time series. And Lawrence mentioned this this example here that the value of the time series at time t is 99% the value of the previous time step plus an occasional spike. So if I'm here, my value is 99% of the previous plus an occasional spike, which could or could not be there. So there's no spike, I'm just 99% of my previous value, and there's a spike. You could have multiple autocorrelations or lags, as they're called. You could have a value that's dependent on the previous time step, but also that's one that's dependent on 50 timestamps before. So in this case, this time series is the value time t is 70% of the value at the previous time step plus 20% of the value at the 50 timestamps before plus an occasional spike. So the smoothing, the first smoothing that you see is coming from the t-1 component here, and these multiple components that you see here, this 1, 2, 3, almost 5, are actually coming from this t-50 component. If you add trend, seasonality, autocorrelation, and noise, you might get actually something that looks like a real-time series or more like a real lifetime series. Not that these are not real-time series, they are more like a real life, I meant. That the value at a given time probably depends on where you are, probably depends on previous values, probably depends on seasonality. Let's say this has a weekly or annual periodicity, you might depend on that. And noise makes it a little bit uncertain so that you don't have exactly the same values repeated again and again. And when we talked about stationarity and non-stationarity, this is something that you clearly see here a trend, some patterns, some seasonality, some autocorrelation, but then something happened at this point, time step 200, that caused it to dramatically change behavior. The seasonality changed, the trend changed, the autocorrelation changed, so this is a non-stationary time series. And the challenge with forecasting in this setup is that you cannot use just the previous historical information to predict future ones. Ideally, you want to include the stationary part of the process and also the one that broke the stationarity, and actually then predict some future values.
Point of clarification on that. I believe that technically the definition of stationarity would make that trends, anything that has a non-zero trend would not be stationary as well. It's the breaking of that trend that makes this time series difficult to forecast. But stationarity, as I understand the definition, allows for things like autocorrelation, seasonality, and noise, none of which affect the unconditional joint probability distribution, although they may affect the conditional joint probability distribution, such as correlation. But a trend, I think, is in itself non-stationary.
Yep, you're right, because the average value, right, changes over time. So
yeah,
the trend breaks the stationary part, correct. Great, then in terms of how do we create some artificial data for us to work with before we start tackling real life data? We can work with a baseline time series. We can add some trend to it. We can add some seasonality. And what we get is something like this, a very mathematical model that clearly has a period, clearly depends on previous values, autocorrelation, and there's a trend overall that is increasing. To make this more real life looking, we would need to add noise. That's random values. We need a noise level. So in this case, we're generating numbers between 0 and 1. We're multiplying them by a noise level that's dependent on us. And what we're doing here is we're just plotting this white noise over time. And as you can see, the values are pretty random, but there's an amplitude effect, or there's an amplitude that they can go up to. In this case, the amplitude looks like 20 or negative 20. So if you want to have a more controlled time series, maybe if you know that your time series doesn't cross a threshold, then maybe you can multiply that by the appropriate amplitude. Something that that Lawrence touched in this week was, okay, so we have this data. How can we split it into training, validation, test set? I mean, in machine learning in general, we need to define a training set where we train our model. Then we need to define a validation set where we actually test our trained model. And then we need to define a test set where we actually use everything that we learned from the training and the validation set into this test data set. So one way to do that is to consider historical information as training set or training period, then some near-term part of the time series as a validation set, and the last part of it as a test set. In deep learning, is if you remember, when we did NLP or when we did computer vision, we actually shuffled our data. In this case, if you do that, you'll actually get even worse results because there is a trend, there is a time direction here. So you can't just pick as training examples something from here, from here, from here, and create your own training validation test. So it's best if you keep training as your archive or your historical information, your validation somewhere over like medium term information, and then your test is your most recent past. Then once you train your model, you can actually consume the training and validation. You can actually combine them into one larger training set and use the previous test set as your validation set, and then use the present as your test set. So basically you're producing now, or you're predicting or forecasting real life values at this point. So that setup was called fixed partitioning because you have clearly defined training, validation, and test set. If your training set rolls over, you have something called roll forward partitioning. All that says is that you start with the fixed partitioning as you are, but then the test and validation is exactly the same as before. By your training now, you don't use the entire training set to actually train your model. You actually start with a subset of your training set. So let's say this partition here. So in version 1 of my model, I'm going to use up till this point to train my model. I will validate it against this validation period. And tune my model accordingly. Then I will include a few more, let's say 1 more month of data. I will validate my performance of my model against this same validation period. I will add 1 more week, 1 more week, 1 more week until I exhausted all my training data. And then I'm basically back to this fixed partitioning. In our example, we're going to use a fixed partitioning in all our examples. It's relatively easy to also do roll forward, but for ease of convenience and coding, we're going to use fixed partitioning. And something about how do we actually measure our performance and how do we know that our model is doing well? Well, we look at errors. So that means the value that we forecast or we predict and what is the actual value. So in this example, in the validation period, our model would predict the value, let's say 50 or 60. What is the actual value? Maybe the actual value is 62. What is the difference? That's the absolute error or error. If we square the differences of errors, let's say we're predicting a week from now. If we square those errors and we take the mean, then we have something called mean square error. There's a question in the chat.
No, George, I was just mentioning about the roll forward partitioning. I didn't want to break your flow, sorry.
Go for it. No, what is your?
So, when you're forecasting, right? Like, if you look at the example here, right? In the first rolling window, let's say our training set is still what 600, right? Mm-hmm. If your training set is 600, we cannot. How would we predict directly 1100, right? So actually, even it's like initially you take a training period of 600, you have a validation period of next 200, and then test period of next 200. And as you keep increasing the rolling, the training period, you keep extending your validation. So it's something like cross validation. You have multiple validation periods, multiple test periods, which you can take an average or weight and kind of get a score.
So you're actually rolling both the training and the validation and the test, you're saying. It's the both windows are rolling.
Right.
I could see that approach as well.
Yeah.
Cool. So yeah, so we talked about the error, the mean square error. If we take the square root of the mean square error, we have something called RMSE, root mean square error. If we look at the absolute values of our errors without squaring them, and we take the average value, then we have something called mean average error. Then if we're interested in how do our errors compare to our data, so some kind of like percentage, how far are we off from our data? So if we take the ratio of our errors with our actual data and take the absolute value, then we have something called mean absolute percent error, if I can remember correctly. Sorry. Yeah, so that's the MAP. Usually we use MSE or MAE in our as our loss function, as our metrics in our models. You could use either of those. And Lawrence mentions that if the further away your forecast is from your actual, the more it impacts your forecast. Let's say you're in your business, and the larger the area is, the more that it impacts you, then maybe you should use something of a squared error version, like an L2 norm, basically. But if the difference of your forecast from your actually that distance does not impact you that much, maybe you can use an MA instead of an MSE. So if that deviation is important to you, then you use MSE. If it's not that important, if you're just interested if you got it or not, then you use an MA. Cool. Any questions about metrics or partitioning?
I think one of the things to keep in mind whenever you're looking at these is evaluating is the smaller the better.
Yes.
What does MAPE stand for again?
Mean absolute error. Sorry, mean absolute error.
No, the next one, MAPE.
Mean absolute percentage error.
Okay, thanks.
One question I have, if I may, when choosing the starting point for the validation period, does it matter where we start? Because if we're looking at the visual representation, it's easier to point it out. But if we are not looking at a visual representation, it's a bit complicated. Are there techniques that help out with this?
Yeah, and I think Lawrence mentioned this, but when you're looking at your training and validation, you need to make sure that your training set has at least a few periods of your data. So if your data has seasonality, and let's say has annual seasonality, then you need to make sure that your model is exposed to at least a few years of data. So that kind of puts some limits on how much validation data you have. So let's say you have 3 years of data and you want to predict what's going to happen next year, then probably going to have 2 years of training and 1 year of validation.
Right. Well, if the data is based off, let's say, day of the week, that's easy, right? We have natural, points for the beginning of say validation period, say next Monday or next Sunday. But if you have a sensor that emits the data every, say, half a second, what time period do you use? What starting point do you use for validation? So you see the question I'm asking?
I see the question, yeah, maybe, yeah. So if there's no trend or there's no seasonality you can clearly see, actually you have to plot it to see.
That's the point. Like, do you always need to plot, or there are mathematical techniques that tell you you can use this as a starting point of your validation period?
I mean, the easiest approach would be to just keep the 20% of your most recent data. You always want to keep the most recent data as your validation period. So you can always do 20% of your most recent as your validation and 80% of your data as your training. And then you roll that over as time goes. But I think there are techniques that can identify if your time series is autocorrelated or if it has seasonality or if it has a trend. So if they tell you that there is a seasonality of, a week, then you want to make sure that you have at least several weeks in your training and at least a couple of weeks in validation.
So do I understand the question correctly then, that it sounds like what is really interesting is being able to calculate a seasonality in the data without having to plot it?
Exactly. If there are any mathematical techniques that I could use and say, this is my data set, go to the end of it and go towards the beginning, and whether it's 20% or 30%, find me enough data that captures enough seasonality so that if I were to use it for validation, I go through kind of all possible combination and my metrics that I'm calculating are meaningful.
Well, I think
without plotting the chart.
Yeah, I think one of the reasons that you want to choose an integer, or that it's optimal to choose an integer number of seasons, is so that you don't have biases in the data based on validating more for summer data than for winter data. If that introduces some kind of bias.
Just like I said, if I'm doing credit card fraud detection, then I can always base it off, first day of the week or first day of the month or first day of the year to capture holidays, business days, and etc. But if you have sensors emitting data such as EKG or something else, how do you do that? Do you always need to plot the data, or there are some mathematical techniques that you could use?
I would advise applying things like autoregressive linear models, where you can essentially, you're fitting a linear regression for, say time step, I don't know, in our validation period, it looks like maybe the first time step is number 700 for validation. So then you can fit, say, an AR 50 series where you're regressing on trying to find a linear regression that predicts time step 700 best based on the values between time steps 650 and 700. And then you can play with the size of that window to determine how far back you need to go to optimize that. And that can give you some hints as to seasonality. You can also do some assessments on correlation, like autocorrelation across. In this particular set, you'll find that the autocorrelation, if you have your points spaced exactly 1 year apart, is higher than the autocorrelation if your points are spaced 9 months or 15 months apart. So,
If you
so
remove
applying
the
kinds of
seasonal thought, if you remove the seasonal thought and remove that type of bias, is what your thought was when you started this. If you just randomize the data over time and remove that, will you still be able to find the seasonal categorization in the data? Because that's what you're really looking for. If you randomize the data and then you choose your data with the idea of randomization without time in there, and therefore then you partition it, as we've been talking about, and therefore train your data accordingly, will you not still find the seasonality if it's still there if you have sufficient data?
So to me, if you actually shuffle the data and you don't respect the time order, I think you're going to have a very hard time finding seasonality, simply because seasonality is defined as a function of time. So it's highly dependent on time. So if you shuffle your data and you say you pick some data points from here, some data points from here, and some data points from here, and you're trying to predict the next value, you're not respecting the order of values, you know, the sequence order.
I'm not shuffling it for showing the time series, but I'm trying to find out if you have sufficient data, the larger set of data that you have should sufficiently show seasonality. If it is true, if seasonality is still there, really, if you have sufficient amount of data and you partition it accordingly, it should still show that seasonality when you train your model, and therefore then you test it. Yes?
Yes.
Okay, I think I understand what you're saying. Yes. It sounds almost like an imputation problem at that point, right? If you mask 10% of the points, can I still determine that there's seasonality in the data set?
Yes. And that's what I thought was the thought when we started this talk, that when you're talking about this type of data, that without graphing it, without seeing it, without understanding it, you need to automatically train your model to find this. Therefore, take a sufficient amount of data. You know it's there. You just have to train your model then to recognize that, to see, can it find it? And that's the real trick when we're talking about this. And therefore, when we're talking about all the error sets and everything else, to try remove the bias that you're talking about, which I don't, it's a difference in data. I don't like the word bias right now. But when you remove that difference in the data and shuffle it so that you can then see, can you still find it? That's the trick in the magic here when we're using this type of prediction model.
Deep learning models, they don't look into seasonality or anything. They just look at the series of data. Like right now, we've plotted this. If you were to look into traditional statistical methods like the autoregressive one, you would look into this plot, try to find out seasonality, and there are ways over there. But deep learning models, we don't specify is there any seasonality or anything. You just give it a series and it predicts, right?
Yeah, we just have to define this breakpoints, right? We have to define where does training stop, where does validation start, where does validation stop, where does test start. The question is, how do you find this breaking point?
So, not a very perfect answer, but when I did, I used this rolling window approach actually, and we had about 72 data points in total. So not many. We had to kind of find a way in which we could test our model effectively. I used LSTM, and what I noticed was I didn't know exact reason, but when I started creating the training period, I did need a minimum of 10 to 12 data points depending on how many values I was predicting in future. Like I was predicting 6 values or 10 values. So based on that, there was a limit of training period that I could start my rolling window on. And if it was less than that, actually my LSTM model was not giving me any output. It was failing. So it was kind of a trial and error method, but I didn't have a lot of data, so I could do it. But yeah, I did see that there was a minimum requirement of training period in that using LSTM.
Yeah.
Yeah, and I tried to correlate it with, because autoregressive models, we were actually looking at the same plot in both the ways, autoregressive as well as the deep learning approaches, and I could kind of relate it because we knew what was the seasonality and AR model, like he mentioned, AR 56. That means we need at least 56 points to predict my next value, right? So based on that approach, if we sum up those values, like, how many previous values I need, what is my seasonality, so that minimum number of training period that I got was approximating those numbers. It was, like I said, trial and error, but there are ways which, if we could relate those autoregressive approaches, we could get a minimum training period.
Got it. Thank you. Cool. So in this approach, we're actually going to find a time in our time series, and we're going to consider everything to the left of it as training time and everything to the right of it as validation set. Now, how do you find this split time? If I understood correctly your questions, if there is any mathematical way to find this, maybe not, to the best of my knowledge. If your data is seasonal, then you want to make sure that you have at least integer number of seasons to the training set. If your data is not seasonal, if it's just coming from a sensor, maybe 80-20 split from just a very generic rule. But then again, as you dive into your data, maybe you see some other patterns that might actually help you find this splitting time. But to the best of my knowledge, I don't think the splitting time is the most important factor in your model. You could have 800, you can have 900, you can have 1200. Worst case is that you break your training and validation meet seasonality, still your model should be able to perform properly. You might just need to fine tune a little bit more, training a little bit more. So in this case, we have a...
Hold on. Can you explain better, why do we need to add noise to it?
That was just so that it's not just pure mathematical time series, that it's more of a real life looking time series, like let's say a sensor reading. Let's say you're reading temperature or humidity. So it's more of a real life time series.
So that you wouldn't add that if you actually had a real life time series.
Absolutely not. You would not. You'd make your problem more complicated.
Right. We're just synthesizing. We're just synthesizing data here, so trying to make it look a little bit realistic.
Yeah. We're using generated data. Exactly. We're using artificial data here. So in our computer vision model, it's like we're using the computer generated images of hands, rock, paper, scissors. If you remember that example, that's from computer graphics. It's not the best real life data, but then again, we didn't have, or Lawrence didn't have the time or the energy to take 3,000 pictures of people's hands. So it's like, okay, let me generate them. So this is just us, trying to get used to different time series without spending the time to actually get real life time series, which will happen in week 4. So one way of doing forecasting is called naive forecasting. All that it does is it actually looks at the previous step and it uses that as a forecast for the next step. So let's say if a series is 1, 2, 3, my forecast for the next step would be the number 3, simply because my previous step was 3. So in blue here we have the validation set, which starts from 1,000, since we split our time series from 1,000, and we're plotting the validation. And in orange, we're printing our forecasted version of it. And if we zoom in a little bit, you'll see that it's just a shifted version of the validation set. So my forecasted value in orange for time series, let's say 1100, is whatever it was for one step before. So if we follow this approach, and if we use these metrics that we saw above, mean squared error and absolute error, we get an average mean squared error of 61 units and an absolute error of 5 units. So this is just to give us an idea of, for this time series, we use this kind of naive forecasting. How far are we from the truth? And our goal is to minimize both of these metrics or loss functions. So there's no deep learning here. This is just mathematical approach of using the previous value. There's no model here. Another forecasting method we could use is called the moving average. That depends on a window size. So all that says is that let's say if we have daily time series, if our time series depends on days and our x-axis is days, if our window size is 30, that basically what we're doing is we're looking at the previous 30 days. We're taking the average of those values. We're predicting that as the future value of the 31st day. That's what we're doing. So if we do that, you'll see in orange is our forecast and blue is actually our validation time series. You'll see that we're kind of capturing the base or the trend of the pattern, but we're definitely lagging behind impulses or significant differences from previous values. So in this case, we have a jump. We're predicting the average of the 30 previous values. So the average of the 30 previous values is about 65. We're going to predict about 65. So it takes us a good amount of time steps to actually get a higher value, simply because this average needs to, this higher values, we need more of them to contribute to the average value. And then similarly, when the time series falls, we're basically lagging a little bit behind, similarly here. So when we do that, we get an MSC of 106. We actually did worse, and MAE of 7. So it was 16.5. We went higher now, which is bad. Another thing we can do is, if somehow we can determine that our data is seasonal, and let's say seasonal on an annual basis. Let's say the value 365 units ago is similar to the value now. We can take the difference of the values now with the values 365 units ago, or 365 days ago. I will assume these are days just to make the conversation easier. So if I do that, if I look at let's say, the values for my week, let's say week of June, compared to values of the same week a year ago, if I look at that difference hopefully is pretty small and doesn't have a trend. You see that it should be pretty flat, the average value. Then what I can do is I can take the moving average of that difference, since this difference is pretty spiky and actually depends on absolute values. But if I take the moving average version of it, think of it as a filtered version or the smooth version of this time series. Then what I can do is I can combine my series with the moving average of the difference. And if I do that, you'll see now that I'm able to capture these spikes, simply because the spikes I know are seasonal. I know that every 365 days, probably I'm going to see a spike. So using that information, I'm able now to bring my error metrics even lower. So we're now at 52 and 5. A better version of this is, instead of doing the absolute difference of the past, is, so let's go back. So instead of adding the value in my time series 365 days ago, I actually smooth it out first. So I pass my time series 365 days ago through a moving average, and then I take the moving average of the differences. So that way I basically take out the effect of noise, because if I do a day-to-day difference from 365 days apart, depending on the noise and depending on which day it is, you might get a high difference. But if I smooth it out first and then add it to my time series, I get much better results. So that brings it down to 33 and 4, which is the lowest for this specific time series. Cool. I know this was more of a statistical approach or more of a just a background, but this is really important for us before we start tackling similar problems using a deep learning approach. So any questions before we move to using deep learning, how to tackle this challenge?
I'll just say that given what we're about to cover, look at those last metrics, 33.4 and especially the 4.5. That's interesting.
That's interesting, but also I have to tell you, I have to keep in mind that when you generate this data, they're depending on noise, right?
Yeah.
Which is random. But yeah, you're right. Cool. David, you want to click away and you tell me?
I'll let you run the slides and I'll do the talking. That'll be perfect.
Go for it. And the floor is yours, David.
Okay, so now we're going to move on from just mathematical approaches to try to use some apply neural networks to the same type of time series. Next slide here. So the first thing that Lawrence goes through is he's going to show how we can generate these time series using some of the methods that are in the tf.data dataset libraries. So the first thing he's going to do is just generate a simple range from 0 to 9 and print that out, and that's our first data set. And then we need to, we're going to take that data set and we're going to generate a window where we are going to shift by 5. So we're going to, if we started with 0, we're going to go 5 from there, 1, 2, 3, 4. We're going to do that until we run out of numbers in our data set. So the last ones you see, they're not 5 as far as the number of values in the window. It cuts off at 9. We're going to then drop the remainders for the ones that don't have a complete set of 5. And he does that with this drop remainder true, and that leaves us with these 6 rows. And if we continue on, we now want to partition these in terms of making them into an actual, like an actual window that has a batch, if that makes sense. It's just basically we're separating each of them into a sample. We'll go on to the next one.
Almost like a list.
Yeah, basically it looks like a list in a sense. And now we're going to apply a mapping that's going to give us a slight different collection. We're going to basically get our features and our labels out of this, or what he calls X and Y here. And what we're going to do is the first 4 entries are going to be our features, and we're going to try to predict our label, which is the 4th position. You may remember from we did how similar this is to how we did natural language processing, where we took our tokens and we did a very similar thing. We took the last token and made those into what we're going to be predicting our labels.
Mm-hmm.
It's very similar to sequence processing. And then to eliminate sequence bias, where the order of the data set, training data set, could make a difference in how things are resolved, we're going to actually shuffle this data set now with a nice little routine that's in there. One thing to notice, he didn't go through it very much, but he just said we're going to use our buffer size, the same set as our data set could possibly be. But in reality, this affects speed of how we shuffle. The buffer is going to shuffle. Typically in a very large data set, you may shuffle like 10,000 at a time. So you put a buffer of 10,000, but you're not actually shuffling the whole data set at once, because that can be memory intensive and slow and possibly cause problems. And then we're gonna actually batch these up so that we can use them in a manner we're used to with neural networks. And we're gonna fetch a batch. He sets the batch size here as an example of 2. So you can see we're getting 2 of the feature sets, their samples. The 0, 1, 2, 3 goes with 4, obviously, in the Y, and then the 5, 6, 7, 8 goes with the label 9. And we're getting batches of two of these at a time. So very straightforward. He's just demonstrating how you can do this very straightforward with the TF data methodologies. I will quickly point out there would be a different way that we could have done this. There's a TensorFlow Keras pre-processing library. I don't know if you remember when we did the image data, we used the image data generator to feed us batches. It was very useful when you had a lot of data that you didn't want to store up in memory. Mm-hmm. There's a similar Keras pre-processing in the sequence folder that's called time series generator, kind of like an image data generator that's for time series. The one flaw is it doesn't allow you to. You already have to have the data in a NumPy array, basically, so you can't just read it off of a disk or a file or something like that. But it does generate nice batches of data for you. I think the advantages of doing it the way that Lawrence is showing is that you can work with structures you'll learn later on in other courses that allow you to do a lot of that, handle a lot of massive data in a very efficient way. Go ahead. So as you know, George talked about, this is our series we're actually going to use. It's the same one we had before, basically, and we're going to split it at 1,000. He's setting up here the window size and the batch size and the shuffle buffer size that we're going to feed into those routines we just saw before to generate our time series. And you can see here how he's doing that. He's just showing you what this data is going to look like. You can see after 1,000, we're going to validate and try to predict that series. Go ahead.
Yeah, and I just try to plot some other variables here, like baseline, amplitude, slope, in case you're interested of how actually was this synthetic time series generated.
Right. All right, as you saw before, he showed how you could use the data set to generate a nice batched up version. He's written a routine called windowed data set where you feed in a series and our window size they want to use, the batch size, and the shuffle buffer, which have all been set in the prior code. Then we're going to look at a very simple neural network. It's going to be a single dense node where we're going to predict our value. You can see here we're just using this same window data set as input. And all we need to provide for input shape for our dense layer is that window size. And the actual, when we do the fit, down there it uses the data set, and the fit, when you do fit with a data set, it looks for the X values and the Y values to be provided by that data set in the batches that you're specifying. For compiling here, we're going to use the optimizer. We're just going to use the stochastic gradient descent with a learning rate of 1 to the -6 here. And we're going to, as expected, we're going to look for a loss of mean squared error. So we're going to show the result. This is basically a linear regression because we're not using any nonlinear activation here. We're just using a simple dense layer. And you see the results are not that great, but we're losses at 50. That's one thing to remember. He did basically, because this is like a linear regression, you can think of he's printing out the weights to show you the weights that would be applied to those inputs, and then the bias, which is that second array there that would also go with that. And we're going to now apply that to our forecasted area, which is that to see what our validation data, how we do on that. We're going to apply that as a forecast. You're just going to do your model predict for that area, and he's going to be able to print that for us. So what he's doing, he's overlaying the validation data that we have with this predicted result. And I think the plot is next. You can see it there. So you can see it's not bad, actually. It's, could be a lot better, but it's interesting that how it compares to some of the statistical methods. And I think, George, did you print out the means? There it is. So there's our mean absolute error. If you recall, the best method that George introduced, the last one was, I think, was a 4.54 or something like that. My memory serves me right. And here we've got a mean absolute error of 5.2, which is not too far off for such a simple neural network. So go ahead.
What I found interesting was the accuracy was 0 whatever. So that means we're never actually hitting the exact value. Yeah, we're maybe off by a little bit. So accuracy might not be the best metric here to track.
Yeah, I'm surprised. I don't think he tracks it in some of the other ones, but yeah. All right, so let's see if we can do a little better. Is there something in the chat here? Let's see.
Sorry.
Oh, sorry. Yeah. we're gonna go ahead and do a deeper neural network here. Basically, it's a denser network now with 2 more layers added in that actually are not just linear activations. So let's see how this compares. We're using the same optimization or optimizer that we were using before, same loss. He doesn't bother showing accuracy, as you pointed out. And you can see we do quite a bit better on our losses down at 38, and when we look at the mean absolute error, we're now down to 4.67. So we've improved.
But just to clarify, I think every time he generates this time series, they're slightly different. So I don't think we can use this as our metric to actually track them too.
It's hard to compare them. I did do some work on this later.
Okay, perfect. Yeah. So the real test would be to actually use the same time series on different models. But in his examples, every time he used a time series, it was slightly different.
Yeah, he's introducing quite a few random things in here. Not just the time series coming in, the data coming in, but actually how we do the.
Yeah, that's why I'm plotting this baseline amplitude.
Is he changing the parameters? It's not just the noise that's changing. It's
if you notice, they're different. The baseline, the amplitude, the slope, the noise level. I think so. Yeah.
Huh. Okay.
That's why I could never find. I could never track or bring this lower because I think it's inherently related to your time series, right?
Okay.
And he also, like you pointed here, David, he's using nonlinearity series. He's introducing the ReLU function, whereas before we were just outputting the linear.
Yeah, I thought that would be worth pointing out as well. If you remember way back to our first meetup when we had a linear function, essentially, that we were training a neural network to do. The first network that you showed here was also a linear function, and it's just basically identical to applying like an AR20 model to the problem.
Right. So then he introduces an interesting concept here, something I still don't really have my head wrapped around, but you notice that when we chose our stochastic gradient descent, we had to choose a parameter called the learning rate, and he chose a good one, but he talks about the fact that that's kind of the dark arts of you can try plugging in 1 million different learning rates to see what the right choice is. There are third-party hyperparameter optimizers out there that can help you in this situation, but they do the same thing. They try a whole bunch of different range of values. And what he does, he provides this idea of using the learning rate scheduler to find out what the correct value that we should choose is. And how he does that, he sets up a learning rate scheduler that's going to get larger by a small amount by every epoch. So you're going to adjust the value on a constant value as you run through the epochs in your learning. And we're going to do this. He did it for I think like 100 epochs, and he started at a fairly small value of 1 there to the e to the -8. And we can see what we get. But the key is this learning rate scheduler is in a callback, which if you recall from earlier classes, the callbacks are basically after the end of each epoch, they're going to be called and they can adjust the learning rate that the optimizer is using. It's being printed out to the right there. The learning rate is just getting adjusted. You can see it's getting larger. And we'll plot that out and we'll look at the loss on the y-axis versus the learning rate. And what you want to see is obviously it go down, but also where does it become unstable? In other words, you're making, if I think about it, your optimizer is choosing what that next step is going to be, and if you get to be your learning rate's too large, it's going to start making a step far away from where the minimum loss is. And so what he's doing is he's choosing a value before it gets to be unstable. So here, I believe, if I recall in his example, he chose like 8, it's 10 to the -6, so something right in there, yeah. which I thought was a little aggressive on his part, but it seemed to work.
Mhm.
So then he goes back and he sets that as the learning rate that we're going to keep, and he's going to run this for 500 epochs and see what happens.
100.
Here you can see he ran it. It doesn't look like it really makes much difference, but if you zoom in and ignore the first 10 epochs and just plot the rest, you can sort of see it's still learning. It's getting pretty violent there for this case. In his example, this is not the case, but I think this is the random choice of that's being used by the random number generator. So George saw a very, I think this is your plot, not his, right?
Yeah, this is mine for Colab.
Yeah, so you saw he has a much smoother plot for this. And again, I think that has to do with the random number generator being fixed. But what we can see from here, though, is there's the fit, and I think you have the MAE somewhere there. Okay, so for this case, you actually got, I can't remember, did you get you got a slightly higher value?
I got 5.3.
Yeah, so again, I don't know if we're looking at the same data because of the way the time series is generated, right? This could be different data, so you don't actually, he showed an improvement in his slides. You don't have an improvement here, actually.
I don't.
So it actually made it worse, which kind of really makes you wonder why you would want to use that technique to optimize your learning rate.
This whole chapter was me going deeper and more complicated and getting worse results.
Exactly. So it's very interesting.
On different time series. Okay, on different.
Yeah, it's
the
different.
baseline of the trains and the amplitude is different.
So my next few slides are going to maybe answer some of this. But so then I think, George, we're going to play around with changing our network a little bit. You changed some of the values there for the time series, I see.
Yep.
But let's sort of that. So here we're just changing some of those values to see what happens. We didn't change our network or our learning rate. We kept it the same, and want to see the results for that.
It's just different data. This is a completely different data series.
Just different data, see what happens. Again, it looks like maybe here it would have been a different choice for that learned value, but here we get a very, very, much lower mean absolute error, but I'm not sure how to compare it to the other.
No, this we can only compare it with the next slide.
Yeah. So then we're going to change our network and keep everything else the same. We're going to make the first dense layer 10 times bigger and see what happens.
Yeah.
More
10 times more parameters.
Right. Very similar look there, but here we get a different result. Not much change at all.
Yep.
Right?
Yep. So this is a fair comparison. Now the data set is exactly the same.
Well, I'll disagree on that, but I'll show you why in a second. All right, so I wanted to look into this further. So I did quite a few more calculations. And, one thing, I thought we brought this up, we may have brought this up before, but in TensorFlow, if you want to get consistent results from run to run, you need to take care of the picking of random number generator, right?
Mm-hmm.
So in TensorFlow, you need to seed this is just an example of some of the things that you need to control. But you can set the random number generator in TensorFlow that's used, and so I've done that. And I've also set the random, when you import random, set that. And that's used by several of the other routines when you're shuffling and if you use sklearn. I think when he generated the time series, he uses actually the just straight Python random number generator. So I've controlled those by using seed. I've also made some commonality. He did, when he set his learning rate, he would do 500 epochs, but when he just set the initial 1 point, or one, I think he used 1, and it was e to the minus 6 versus 8 e to the minus 6. On one of them, he only went 100 epochs, and then one he went 500. So I'm going to set them all to 500 to be the same, right?
got it.
And then each run in collab, this is particular to collab, but I'm going to restart the runtime and run all on each test. So I'm going to.
So just have a question about the seeds.
Yes.
So we have, we're setting a seed in the random module, and we're also setting a separate one in TensorFlow.
That's right.
Yep.
The underscore is
I
not.
seem to recall reading somewhere that if you're using NumPy, it has its own random number generator as well. Is the TensorFlow one kind of piggybacking off of that, you know?
So I think it's the other. I think that NumPy is using the Python one. I could be
NumPy
wrong.
is using the Python one.
I could be wrong. I've seen people set the NumPy one also. But yeah, I think one of them, they're tied, they're repeating it.
So, I mean, there's two sources of randomness in our problem here, right? There's the data generation itself,
yeah,
because it's synthetic, and the neural network weight initialization.
That's right.
So I'm guessing that the TF random set seed is maintaining consistency for the initialization, while the other seed is making our data consistent
for the time series generation. Yeah, that's right. Right. So I found that setting these two gave me consistent results. And so I'll show you in the next screen what I mean by consistent. So
I think TensorFlow has their own seed as well, right? I don't think it exactly this. I don't think it's enough to just set up random seed or NP NumPy seed. I think you also have to set up the TF random seed,
which I did here, right? So,
yeah. And then restarting this runtime. So you before every run you restart this, or you just restart in the beginning and run different tests?
No, I restarted the runtime every time because I didn't want any model, prior model things in or any. Yeah, you may not have to do that. I just force a habit. I just wanted to make sure.
I introduced one more screenshot because you use it later. I thought it would be nice to introduce it here. What exactly is this callback?
Oh, okay. Yeah. So so when he did
another, by the way, on that restarting the runtime, I can't remember the method off the top of my head, but there's another method that he introduces at some point later in this course where you kind of clear out the model parameters so you don't have to restart the runtime each time.
Yep. And that's typically, I use that a lot when you want to change your model definition in the same code block and things like that. It's very important to do that. Yeah. So what Lawrence was using for figuring out his learning rate was he was using a learning rate scheduler where at each epoch he made an adjustment to the learning rate based on a mathematical formula. What I'm using is a different callback that's in TensorFlow and Keras that reduces the learning rate when you're a metric, or basically a metric that you're monitoring stops changing at a certain factor, right? And what I'm monitoring, typically in this case I'm monitoring the loss because we don't have a val loss, and the mode here is auto. So loss is looking for a change. That means it looks at the name of the metric you're monitoring, and loss, when it sees loss in the name, it's going to look for changes that are going negative, right? So as long as you're continuing, the losses continuing to go down. Patience tells you how many epochs to watch for. So if after 10 epochs, the val loss here, but in my case, loss, is not going down, it will then lower the learning rate automatically. So it's going to reduce that learning rate automatically by a set amount. And you're going to, by the factor actually there, yeah. And you're going to continue to do that until you reach the minimum learning rate, which in this case is just, nothing.
I like this. It's more of a dynamic learning rate control instead of the sequence-based or equally spaced learning rate that we had before, where it was just increasing by the same factor. You're actually looking at the loss, and if it hasn't changed for the last 10 epochs, you reduce it by 10.
That's right.
Yeah, this is very much like data-driven annealing, I guess.
Similar, very, very similar. Yes, yeah, absolutely. So the idea here was I was going to look at the different ways. So the first line here is his original model. Again, he ran it for 100. I ran it for 500 epochs to make it the same, but I didn't change any of his learning rate or anything like that. And I just plotted out what the mean absolute error was. That 4.5 looks very, very similar to what we saw in week 1, at the end of week 1, right? Different data though, of course. But the idea is with doing the things that I set for consistency on the prior page, every time I run this, I will get exactly that value.
Oh.
Right. So that's what I was looking for. To be able to compare these things, I want to take out any kind of randomness, right? I want to make sure I'm getting, because otherwise you don't know what you're learning, especially with these small changes.
Nice.
David, just to clarify, that's because the random number generator is seeded with 51, and the sequence is, while pseudo-random, is by and large predictable.
It's it's exactly
right.
predictable.
Is it beneficial to use a large prime number for a seed or no?
Good question.
I think that the functions that underlie the pseudo-random generators are unpredictable. I mean, that they're essentially doing large matrix, large multiplications on numbers and adding other numbers. I don't think it's supposed to make any difference, really. There should be no systematic preference for having a seed that's prime or a seed that's small. Okay, at least assuming that it's pseudo-random.
Right. So that's how I got that. And then number 2 was basically given this random set that I was using, I looked at that learning rate scheduler graph and picked off a number that I thought was where it should be, because my graph is slightly different because my random numbers are different. So in this case, he had used 8 and I used 4 there. So just to see if I could get the best result. So that was supposed to be the optimal. You can see there's not much change from number 1 and number 2 as far as the learning rate, but I got an actually worse value. So again, I was using his exact method to try to choose the learning rate and didn't do as well. Now, maybe if I had no idea what to choose for a learning rate, it would have been a pretty good choice, right? So if I had the universe of numbers, it would have helped me figure out a number to use, clearly, even though it wasn't the best. So then I tried using a different optimizer, one I use on a very regular basis. I just used the default learning rate parameter here for Adam. It didn't work that great. It's not that far off. Probably, there's ways I could have improved it, but I consistently got that.
Are the learning rates comparable to Adam and SGD? Like that learning rate there is 3 orders of magnitude higher than the one that was used with SGD.
Yeah, I think they're not comparable.
Yeah.
I think they're very different.
So I have a quick question.
Adam will change the learning rate based on first order and second order momentum. So this is just the initial learning rate.
That's just the initial learning rate.
SGD will keep it the same.
So for these, you locked your seed in and then just did these once, correct?
When you mean I did them once?
So you locked your seed to 51 for each of these, and then you did. So if we just look at 1 and 2,
yes,
you ran it once with Eden -6 and then 40 -6.
Yeah,
on those.
To compare.
Okay, so I was just wondering, because if they were using different random numbers, it could be that I was wondering if it could be that like the randomness that you get from seed 51 may have ended up working better for one than the other if you did each of these like 100 times. Of course, it might take a long time to do that. And kind of took the average MAE of each run, if what the odds are if you thought that possibly 2 became as good or better than 1. At that point, it was sort of unlucky as it's kind of ping pong balls jittering around trying to learn the right values.
That's right. You're right about that.
Okay.
But if I understood correctly, locking those seeds means that you can run number 1 10 times, you're always going to get the same result, right?
Yeah. But so what I'm saying is, so if you think of it trying to learn, it's kind of like trying to find those like minima values or the closest value. So it's kind of bouncing around a little bit, saying, oh, I need to go a little to the left, and it moves to the left. Oh, I need to go a little bit to the right, it moves back to the right type thing.
Yeah, I think if I understand what Will's saying is, did I run them in basically separate sessions so they each got that first seed, right?
Well, I mean, so if each time you run it with so if you ran it with random seeds instead of seed 51 and you ran number 1 100 times, you might get 4.500, you might get 4.8, you might get 4.2. I don't know what kind of ranges if you did a check like that at all.
Right, this is just one sample from the
yeah.
whole distribution of values that one could get.
If that kind of randomness of 51 here happened to be good for optimizer 1 and not as good for optimizer 2, it could be, I was just checking to see if I was correct in my thinking about how that would work, that it could be sort of that this was an unlucky randomness for one of the optimizers.
It could be. I would hope the optimizers are a little bit more robust against the initial weights, but maybe they're not. I was hoping really that it was affecting our time series so that we're looking at the same data. If that makes sense.
Yeah.
Okay. Cool. Okay. Thank you.
Yeah, you're generating noise, so by default you're going to have a different time series.
Yeah. So I was just hoping maybe to stabilize that. But you're right. Obviously, the initial weights are dependent on that random seed, and who knows if we've got them right or not.
You can specify your weight to 0, right, or identity. You can maybe hard code your initial weights to 0 identity.
Yeah, and eliminate that. That's maybe possible. Yeah. So the last one, I just applied this other callback for reducing the learning rate on the plateau, and you can see it actually ended up giving me the best result, not by a lot, obviously. I did want to see if this was a consistent result, so I did actually change the seed and run this again. If you want to go to the next slides. So here I changed it to 52 just to get some different values. Same test again. And if you go to the last slide.
It's becoming a hyperparameter now, David.
I know. my grid search. Yeah. So you can see again.
I'm sure there are quite a few researchers who do grid search over random seed.
Okay, virtual machine running on Google Cloud versus AWS on a sunny day on the West Coast.
Right. You know that the papers are always published with the typical results.
But it was interesting, number 2 there, where I've run the learning rate scheduler. It actually got a different optimal learning rate to use. So did that make much of a difference? It actually got a lot closer. The MA between 1 and 2 is now really, really similar. Again, we got a slightly better value on number 3, and then number 4 again was the best result. What I also wanted to point out with these results is this is a really small neural network, very simple. These things you may see a much larger difference in what I've seen in my experience applying these type of things for a much bigger neural networks. The optimizers can have huge differences depending on the learning rate you choose. If you use some kind of annealing, as Robert said. So again, these numbers for the MAE are not much different, and so like I said, a bigger network might see a bigger change in these.
Awesome.
I have a question about the learning rates.
Yes.
So with the SGD, they're stated as 1e, the -6.
10 to the -6.
10 to the -6. So that's basically 5 zeros and a 1, right?
Yes.
Okay. But that's quite different from with Atom when you use 0.001 or 0.01. So I was wondering why the first ones were so low compared to the others.
So it's the way the optimizers are programmed. They're different. They're not comparable learning rates. In other words, what you're adjusting in the stochastic gradient descent is very different from what you're adjusting in Atom.
Okay.
If that helps. And Atom's doing behind the scenes. It's actually, I think it's actually adjusting based on a bunch of momentums and adjust the learning rate automatically by itself. I don't know if anybody else kind of if anybody else had any thoughts on what Lawrence is doing with choosing learning rates with that rate scheduler, other than giving you an initial ballpark. Because to me, it seems odd that you're doing an actual set of epochs. You're applying, you're going through and you're going toward the minimum, but at each step you're increasing your learning rate. So you're actually taking bigger steps toward the minimum, and then at some point you're just going to drastically overshoot it and get.
Yeah, I would have thought you would go the other way.
It does.
You would make them smaller. Yeah.
It does seem odd that means that's the best choice you could make. But I saw it as a good way to get a ballpark for maybe that, but I didn't know if I was missing something.
No, I think this was like, what is a good exhaustive search we can do on learning rates, and what are some good numbers we can pick. And I think the most important is, where do I identify stable versus unstable behavior? I think if you picked any other numbers here, I think that'd be almost
pretty good.
The same, yeah.
Okay.
What I've seen online is, the plateau one, but also something called hot or cold start, where you basically in the beginning have where the usual way is to have a high rate and then significantly lower it. But I've seen some other approaches where they start with a value, they increase it based on some conditions, they reduce it after that. So I think it's more related to your plateau.
I've seen that a lot with pre-trained models.
Yeah.
It's almost the de facto way to use pre-trained models is you actually ramp up the learning rate and then down after a certain amount, and there's criteria around that.
Actually, I attended a meetup from H2O, and they actually, Data Robot, and they were using another rate scheduler. And I remember I was looking at that paper. I will find it and post it on Slack, but that was a paper on learning rate, and I think it went over this: when do you increase and when do you decrease your learning rate based on your based on a metric.
Yeah, I think I remember that also. Yeah.
I always thought the rule of thumb was that, a higher learning rate, you would move faster, but you would, tend to get stuck more. And so that's why you slowed it down so you could settle into your minimum. So I thought that was sort of the motivation for something like Atom, where, you start kind of high and then settle yourself in. So early on, Lawrence was, seemed like he would talk about he'd look about, one of the things that he would look at was not only accuracy but also training time, and he seemed to be optimizing on that. Like I forget the examples, but he would he'd go, well, our accuracy went up by a percent, but it took 10 times longer here, so we might go the other way. We might accept the lower accuracy for the faster speed. And that was I had the same concerns you did, David. So I was wondering why he went in that direction. To me, it looks like from that graphic that's right there on the screen, you could have made it a lot smaller. The learning rate could have been a lot smaller, and it would have been more stable, it looks to me.
Yeah.
And but maybe it would take a really long time or
I
something.
think the thing that motivated me was that he showed it as, oh, this is a way to get a better result.
Yeah.
But when I did the calculations, it seemed like I wasn't getting that result, and it turned out to be because of the random number generator, right? I mean, it was like, okay, sometimes I got a better result with his learning rate than I did with the initial learning rate, and then sometimes I didn't. So
No, I understand. I think his experiments are poorly controlled, and he increases the number of epochs too. You know, kind of dramatically, and
Yeah, that was
that's
interesting.
sort of a hyperparameter in and of itself.
Right.
Oh, thank you. That reminds me of the paper. So I was able to find the paper. I posted it on our chat. I'll post it on Slack as well. But what this paper basically talks about is you're trading off, you're letting this algorithm control the learning rate, but you don't control the epochs anymore. So you have to give up something. Mm-hmm. So I think this algorithm strives to find this underfitting, overfitting curve where the optimal solution is basically to stop where your validation error doesn't shoot up. So I think you're giving up, you don't know how many epochs you have to train for, but you know that the learning that you're getting from this algorithm, I think it's in some way making progress towards reducing your loss in both training and test. And then the way to stop here is you do some kind of you check basically when this increases or when it stops decreasing, that's when you stop. So you combine this algorithm with some kind of a callback that when your loss doesn't decrease anymore, you stop training.
Yeah, I usually use early stopping.
Yeah, early stopping, exactly.
Yeah.
I was hoping it could be an interesting chart here, but I haven't read the paper. I just came across this algorithm on that other event that I mentioned. Yeah, maybe we can explore this. But if I look at the title, it says part 1, so maybe there's a part 2 on different hyperparameters.
Another general question is why does accuracy seem to be irrelevant here?
Because it's very hard, I guess, to actually hit the exact value, right? These are real numbers. So it could be 3.5, it could be 3.6. You know, accuracy is you didn't hit it. That's why you don't. Accuracy means you either got it or not, right? In this setup, that's why we don't look at the same metric we used to use before, like accuracy. We look at the difference between our forecasted value and the actual value.
Yeah, this is the first time in this course that we've used neural networks to solve a regression problem rather than a classification problem.
Thank you. That's better said. We used to do classification. Now this is regression. We're predicting a real value instead of a label. Cool. Any more questions? Cool. Then just to wrap up, sorry.
A question, if I may. Before they fed the data to the neural network, did they try to say bucket the data into a window, apply a log function, or anything else, make the numbers between, let's say, 0 and 100 on 0 and 1?
No, that was another thing. He didn't scale it. Yeah, he didn't apply scaling. So that was another thing I was thinking probably could really drastically improve our numbers, but yeah.
Thank you.
So there was a training and validation period, but no, there was no scaling on the y-axis.
Thanks.
You're welcome. Any other questions? Great, then wrapping up, as I mentioned, this was our first event on time series. We'd love to have you again on next week when we use recurrent neural networks and convolutional, 1D convolutional to actually tackle similar, exact same problem of forecasting in time series. That will wrap up the last course, and on the specialization, I'll actually complete the specialization. We have a happy hour scheduled as well, and in 2 weeks to kind of celebrate our progress, learn better each other, and then there won't be any slides or any presentation there, just open floor for all of us to get to know each other better. And the week after that, I put an event for how to prepare and pass this TensorFlow developer certificate. So I've mentioned it multiple times that taking this specialization and going through our sessions, we have our deep learning trivia as well, and also our GitHub that I'll mention when I talk about this talk. We are in a perfect position to take this certificate, and I'll go over what is required, how to best prepare, and some tips on how to pass this certificate. with that said, this is it. Thank you everyone for joining. We appreciate it. Again, if this is your first time, all our sessions are recorded. You can find the link on our YouTube channel here. Yeah, spread out the word. Let us know what you think, and hopefully we'll see you again next week. Thank you, David.
Thanks, everybody.
Thank you, everyone, for your questions.
Thank you for diving into the into that analysis in much more detail than the course itself covered. It's very helpful.
Yeah, that was awesome, David. Thank you. Good. Cool. All right, everyone. Have a good night.
Thanks a lot.
Thank you.
Bye-bye.
Bye.
Bye.